Okay, relativity 2 is a little bit of extension. So we did time dilation, right?
Yeah.
We sent Panisse to space, and what happens to time when you're traveling fast?
It's slower.
It slows down, but do you notice it being slow when you're in the spaceship?
No, you don't.
Seems to be the same.
But somebody else
But
observing
relative
it.
to us, time changes.
Yeah.
Okay, that's special relativity. Something else happens. Yeah, can you flip the door closed for us, Panisse? Thank you. Something else happens too. If you sent me to space and I'm flying along, let's say I'm in a spaceship and I go past you guys. If you could see into my spaceship, what would you see happening?
Slow.
I would seem to move in slow motion.
Hello, guys.
And I would see you guys doing what? Everything in fast motion, right? Something else happens as well. So time dilates for me who's moving fast, and also my length contracts. Because I'm moving, right? So if my time is slowing down, the universe has to stay the universe, so a meter becomes less for me in the direction that I travel. Okay, so my time stretches out, and if that happens, that also has to mean that my distance shrinks.
Is that why it's possible, maybe, to travel through space?
Well, there's a lot of implications to it.
Go to another galaxy.
So this is the time dilation formula, yes? Which one is proper time? TO. Is that in the spaceship or on Earth?
In the spaceship.
This is in the spaceship. Length is the same, except it's the inverse. So this is length contraction. Oh, wow. Length contraction. I don't know why I just started writing length contraction. Can you read that?
Yes. Yeah.
Okay. Yeah, so this is time dilation, length contraction. So instead of the proper length being over the Lorentz, it's multiplied by.
Okay.
So your length on Earth is less. It shrinks. Okay. Well, sorry, not length on Earth. My length visible to you would be less.
Right.
So this is what it means. If I'm shooting by you on a spaceship,
It's actually gonna be so slow.
for me, everything looks normal, right? My length, everything's normal. But you would see my spaceship,
So slow.
Kurosh just went like this, and that's true. So my spaceship would appear to you to be shorter than it was.
But not by a lot. Makes sense.
It'd be good diet for me, right? I'd be squish skinny. But not to me, Joshua, that's right. To me, everything would look normal. But what would you look like?
We would look like
It's like mass.
You guys would be like that Instagram filter that my daughter puts on me, where your face goes like this, right? You guys would all be stretched out. But not up and down, that's fine. Only this way. Why only this way?
Because time travels.
Traveling in?
That's the direction I'm traveling in.
But
If you move this way.
Yeah, if I was moving this way, I would appear short this way, and you would appear stretched diagonally. That is length contraction. Let me be clear.
Oh.
Be clear.
What is that for?
Oh, it's David, be clear.
Let me be clear.
You know what David's saying?
No. Tell me.
I'm pretty sure Star Wars used this mechanic when they did the hyperdrive scenes.
Oh yeah, and everything goes.
Yeah, all the stars are stretched.
Yes, exactly. Yeah. Not that Star Wars should be your basis for theoretical physics,
It's
but
pretty
yeah, it's definitely very accurate. Be clear in the concept that the spaceship is not being squished, and you are not being stretched out.
It's just relative to the.
Length itself is being squished. When you move faster, a meter is still a meter, but length itself is squished when you move fast.
A meter is space.
So, here's a question for you.
What speed does it have?
And this is a question that IB will give you. Let's say you have a tunnel, okay, in a mountainside. This is like there's peaks in a mountain, and the tunnel comes out over here, right? And let's say your tunnel is 100 meters long.
Yeah.
And you have a train. These are the train tracks coming out of the tunnel, okay? Get it? Your train's gonna go through the tunnel. But let's say that your train is 125 meters long. Okay. There's your train, the windows and everything. Let's ask the question. Is there a speed at which your train can travel and it will all be inside the tunnel?
Yes. Yes.
Okay, one is to calculate.
Wait,
Sure.
Yeah.
Calculator.
Right there.
How fast do you have to go?
So the train is inside the 100-meter tunnel.
Yeah.
Like
It's
all
gonna
of
go
it.
through the tunnel, right? So is there a point where a 125 meter train will be all inside of a 100 meter tunnel?
Which one is the proper length?
You tell me, what's the proper length?
LO.
Is that the train length
Train.
or this
Train.
length?
Train.
The LO is the proper length, which is the train length. So this is LO.
And then L is unknown.
The speed.
No, L is this.
100.
100. Yeah.
100 is
So if we're standing here watching, what we want to see is we want to see the train shrink, right? We want it to shrink to 100. So what's the speed we have to do where L naught becomes to us 100 meters? This is your 125.
And then what is
C is the speed of light. So don't worry about calculating V, just calculate V over C.
Oh, thanks.
Just give me a percentage of
0.0.
0.6? Did you say 3 over 4?
3 over 5.
3 over 5, okay.
0.6?
So if you solve this, V over C is equal to 3/5. So that would be like right around 2 times 10 to the 8, right? So it's not that fast compared to the speed of light, but really fast compared to anything that human beings have ever done. They've never approached that speed. So you gotta be going fast. But there is a speed where you can fit that train in that tunnel. The way that IB has asked it in the past is they've said, you have this tunnel and it has gates, sharp gates that slam down. And they're saying, how fast does the train have to go? Is there a speed that the train can go so that the gates can slam down and the train will still go through the tunnel and not be harmed?
Why they're so evil? Why they want to stand on the door?
Well,
Yeah.
no, because if it slams down, that's
And there's all kinds of like troubles with that analogy because then you gotta calculate the speed of the gate and it's gonna be relativistic and all that. But we don't worry about that part.
assume instantaneous.
So they usually give you some form of the tunnel question. The other thing that they're gonna give you is a magnetism question. And length contraction has an interesting connection to magnetism. We know that magnetism and electricity are connected, yes?
Yes, sir.
Okay, so how does that work? Well, here's what happens. I'm hoping everybody can see this. Let's say you have a wire. This is a wire, okay? And let's say that your current, this is the weird part of electricity again, right? And IB will ask it this way to try to trip you up a little bit. If I put a current through the wire to the left, what does that actually mean?
Electrons are going right.
Good. Good. Electrons are all going right. and they have some kind of drift velocity, yes? So the E's are all moving to the right.
Yeah.
If I put an electron moving to the right as well, alongside that wire, tell me using the right-hand rule, will it be attracted or repelled?
With right hand.
Wait, what?
So you're right to use your right hand. The current is going to the left.
Yeah.
On top of the wire is the magnetic field coming in or going out of the page?
Out.
It's going in.
Oh,
It's
okay.
gonna pull it down.
So this is going to be traveling through
That's going up.
a bunch
No,
of
yeah.
X's, right?
Oh, it's down.
Okay. Now you have a field coming out with your left hand. If you want to use your left hand for electron, it's moving that way. It's going to be pushed
Out.
up.
Oh.
Okay. Think. Did we do that right? Current in, and your other right hand rule, left hand. Oh wait, no, I didn't use my left hand.
It's downwards.
It's downwards. It's downwards. It's downwards.
What?
Yeah, it's downwards. Because you have to use your left hand because this is.
No, but the current is that side.
Doesn't matter. The current creates the field, right?
Yeah.
So the field is going into the page. So when this charge moves through this field, it's not a positive charge. If it was a positive charge, it would go up. But it's a negative charge, so it should curl down, right?
I forget, but electric.
So the question is, why does that happen? And the reason is because of length contraction. So,
Really?
yeah, really. The electron is moving the same velocity as the E's, right?
Yeah.
Does this have any effect between the E's?
No.
No, why not?
It's no variable.
They're the same speed.
They're going the same speed,
Yeah. Okay.
right? So their velocity relative to each other is 0, everything's just the same. Does this have an effect between the electron that's moving and the protons which are stationary?
Yeah.
Yes. What happens to the length here?
Longer. No, short.
Kurosh is going,
Yeah, short.
length contracts because he's moving relative to the proton.
Yeah.
Okay, now this is a weird thing. What that means is that the concentration of charge is greater between the protons and the electron than it is between the electron and the electrons.
Oh, because yeah.
Wait, what?
You can also think of it the other way. You can say, well, how about we just say that all these electrons are sitting still?
Yeah.
And really, the wire and the protons are being pushed that way. Okay, well then these two, they all have the same normal size of an electron.
Yeah.
But the protons are being
Squeeze.
young, right? Is their charge changing?
No.
Nope. Charge stays the same. Charge is not affected by relativity.
Yeah. That's.
So if you squish a charge,
Becomes more dense.
that's right, your charge per meter, you could call it, is greater. And so the attraction between negative and positives
It's
Becomes greater.
becomes greater because the charge density of these protons relative to this guy
Becomes higher.
is greater than the E's because the protons and this electron are moving relative to each other. These electrons and that electron are not moving relative to each other.
Oh.
And that's why this guy gets attracted. So, let's see if we can, well, you try, take 10 seconds, turn to there's somebody around you and try to explain what I just said.
So basically, the protons are moving right, they're moving to the left, right? And let's say that like the relativity goes. And so basically, since the
There's
protons
more
are
of it in the
moving,
smaller
they're
ones.
contracting.
Yeah.
Right, the protons are contracting,
Yeah.
which means that the amount of charge is also being contracted into a similar sort of space. The charge stays the same, but the charge but it's in a more dense.
The charge per set, like
Yeah.
per little meter.
Yeah, it's like if you switch this eraser down like to really, it's just still the same amount of eraser, but it's just being switched so there's more eraser per square meter. Right?
Yeah.
And that causes an attraction between the electron.
Did you miss or did it go in?
No, I hit it. But I think the cat flew somewhere.
It's fine.
Yeah, I figured.
Charge?
No, there isn't more charge.
Charge density. Charge stays the same, but it's squished. So this is a tricky bit of concept, right? And they will probably ask you about this. They want you to understand that magnetism. So you've always thought of magnetism as this like separate force, right? Magnetism is just electrical attraction and repulsion that happens because of special relativity. That's all it is. It's just electrical force that's increased or decreased because of movement, because of length contraction. So because the electrons and protons are moving relative to each other, they have a relative velocity, their charge density is increased.
Well,
Their charge is not changed. What does change?
Density of it. How much of it there is in the tank?
Yes.
they're like,
If your length is contracted and the charge stays the same, then your charge density goes up.
So it's intensity gets higher?
Density, charge density.
Yeah, but like the intensity of the attraction gets.
Yeah, that's right. That's right. Yeah. So because your charge density is increased between the protons in the wire and the lone electron that's moving past, and that happens because of the relative velocities, then you have the electrical attraction is increased.
so magnetism happens because of special relativity.
Or is this electron still repelled by the electrons in the wire?
It's still.
But not as
Yeah.
much
Not
as
as
it's
much.
attracted to the proton.
Exactly. Thank you, Joshua. Roche. So you still have some repulsion, but the attraction becomes stronger because of that increase in charge density, and that's what pulls our electron down.
Yeah.
Now you could say, okay, fine. What if I put a proton in here instead? No more electron. You huck a proton in here,
Is the proton moving the same?
and now it's moving.
It will
So
be,
what happens now?
it'll be pushed away because of the protons.
The proton and the electrons in the wire are now not moving relative to each other, right?
Wait, the electrons
But
are
the
not moving.
charges of
No, the electrons in the wire are still moving. I'm
Yeah.
still putting a current through.
Yeah.
They do attract each other, but then the charge density of the electrons in the wire is too much, so they. Oh no,
No,
it's
the
too much. They
protons.
attract.
Say that again. This has relative velocity now to what?
Proton.
The electrons or the protons?
The protons. Because
Right.
the protons are moving.
Joshua? Proton and electrons moving together, right?
They have
So do they have a relative velocity?
No.
No, they don't.
If you and I get in if you're riding a skateboard and I'm riding a skateboard, we're going the same speed.
We don't have those.
We do not have relative velocity, but do we have relative velocity to the others in the class?
Yeah.
Yes. So that's what's happening here. You're out here and I'm in these electrons, and we're going no relative velocity. But I do have relative velocity to the protons, right? So is there going to be length contraction?
Yes.
Yes. So is there going to be increase in charge density?
Yes.
Yes.
It would be
Does that produce repulsion or attraction?
Repulsion.
It's going to produce repulsion because suddenly I have this increased charge density between positive and positive. So which way is my proton going to go? It's going to go up. And that works with our right hand rule, right? When the field's going in, my positive charge moving to the right, it's gonna push that.
The other left hand.
Yeah, the other left hand rule, the right hand rule. So magnetism is just electrical attraction and repulsion that is emphasized by special relativity.
That's so neat.
Yeah, it's neat. They will ask you about this, and they'll probably ask you a tunnel question, and they'll probably ask you a simple time dilation or length contraction. The only other thing you probably should know is relativistic addition of velocities, which we will do another day. So that was relativity 2.